let's do it now. Okay, so in code cells you can write Python code like you would in any other environment. And so you can import modules like this. And again, to execute this bunch of code, you press either the run button up here or shift enter, and it's going to run this code. So we can define a variable. We can find another variable. The last variable that you just write down, it's going to print out. So you could either do this, or you could do something like this. So we're in Python 3. Same thing. And you can do simple operations. Now, a little bit confusing, but also kind of cool is that you don't have to work chronologically. So if I assigned a to be 10 up here, and if I say a equals 12 now, and see what a is, it's 12. But if I go up here now and see what a is, it's still 12, right? So it works sort of chronologically, but not from top to bottom. So you can see there's these numbers here, and that's the way the code has been executed. So this one first, and this one, this one, this one, and then this one. So you have to sort of keep track of it. And it can be kind of cool to be able to use this, but it can also be kind of confusing. So if you go back up in a Jupyter Notebook, always remember that your variables that you changed later are still going to be changed. Okay. So there's just some basic functionality here is you can plot in line. So that's really cool. And if you use Jupyter Notebook, one really important thing to remember is if you're inside a function, and often you're using a function you don't really know, well, what are the arguments to that function? If you press Shift-Tab, it's going to come up. If you press it once, it's going to come up with all the arguments. And if you press it twice, it's going to come up with the entire doc string. So that's really handy. You don't need to go to the documentation or everything. If you use a proper module, they all have doc strings, and it's going to tell you what arguments to use. And yeah, you can plot in line. We don't need that. And yeah, in this notebook, there's also information on sharing a notebook. So if you want to have a notebook and you want to share it, there's some things, and how to do remote setup for the notebook. Okay, so that's just as a basic introduction. You can go back to this later and play around with it when you actually do your own work, or you just ask me. Okay, so let's get started now. So we're going to skip the demo notebook. I confused a lot of people with this here. Sorry about that. But hopefully everybody got it figured out in the end. So let's get started with what we actually want to do. Okay. So the first part of this is we're going to code up the simplest machine learning algorithm, linear regression, from scratch in Python. Okay? And that's going to give us some insight about what a machine learning problem actually is. And it's also going to help us understand what a neural network is, because it's really not that different from linear regression. So machine learning is an algorithm that learns to do a task without being explicitly programmed. And we're going to look at a specific subset of machine learning. It's called supervised learning. And in supervised learning, you have an algorithm that learns from labeled training data. So you have a set of data where you know what the outcome should be, and the data you use to train your algorithm to then apply to data where you don't know what the outcome will be. I stole much of this lesson from a really fantastic online course, Fast AI. So if you're interested in getting more into machine learning, I would really recommend checking it out. But let's get started now. Okay, so first we're importing all the modules. So this is how you would use any normal Python script. You first need to import everything that you're going to use later on. And we're going to want to do linear regression, right? So we define our linear regression function, and that's simply we have a parameter a, that's the slope of the line, and b is the intersect. So we're going to define a little function that takes a and b and some values x and returns y basically. And so our goal in this exercise is to learn the parameters a and b of this linear line. Okay, now let's choose the true parameters. So this is sort of the what we want to get at. So we have a equals 2, b equals 4, whatever, doesn't matter. And we can also now create some data points which lie on that line. Let me just do something real quick. This again. I want to take away what I'm doing here. Okay, so we're going to create 50 random data points, x's, between 0 and 1. That's what this numpy.random.rand function does. And then we're going to create the corresponding y's by passing it through our linear, through our line function. And we can plot this then with simple scatter plot. And it's going to look something like this, right? So this is some x's here between 0 and 1. And these are the corresponding y's for our parameters a and b. Now, these are the data that we have available. And from these points, so these are pairs of x's and y's, we want to learn the parameters a and b, given that we don't already know them, right? And so the first step for this is to define, well, how do we define what a good fit would be for our parameters? And for this, we need some sort of error metric, like how far are we from the true solution? And we're going to define the mean squared error as our error metric. So that takes the true y's, and the true y's come from our training data set, and then we're going to make some predictions, right, for y's. And we're going to feed them to this function, take the square of the difference, and take the mean. So it's a simple mean squared error. Now let's start up with some random guesses for a and b. Let's just choose those and scatter those. So this is now still our true values, and these are our guesses for the same x's, right? We have the x values, and based on our guesses for a and b, we're gonna compute the y values, and these are the orange ones here. Okay, and now we can compute the mean squared error. So we simply pass our true y values in here, and these are our predicted y values, and we compute a value, and it's 2 point something, and that's our error now. And that's the error we want to reduce, right? So if we get this error down to 0, we have a perfect fit to the data. Now we could, of course, change these values up here. So we could change a to be 2 and see if it gets lower. No, it doesn't actually. Bad example. So we could play around with this, but that's of course not very satisfying. We would like to have a sort of an algorithm that does this for us, right? It figures out which way do we have to change a and b to get this mean squared error down. And we can write the mean squared error as a function of our line. So we simply plug in our line function to the mean squared error function, and that's, in machine learning, you call this sort of the loss function. This is always something that you want to reduce. So loss function is anything that gives you a lower value if you get a better fit to your training data. So our loss function now takes the true y's, it takes the parameters a and b that we're currently guessing, it takes the x's, and it simply computes the predicted y's and computes the mean squared error. Okay. All right. So now we want to figure out how do we have to change a and b in order to get this loss down. And you do this simply by differentiating. You compute the derivative of the loss function with respect to a and the derivative of the loss function with respect to b. And because this is a simple function, we can do it analytically. Even I managed to do it after some playing around. And so you come up with equations like this, right? So these are our derivatives of the loss function with respect to a and with respect to b. And now the derivative points in the direction up gradient. So if we go a step in the negative gradient direction, we should get a lower loss. And this is why this algorithm is called gradient descent. And the step size is determined by the learning rate. Okay, so we can also draw this as a diagram here. So if this is our parameter a and parameter b, and we're drawing our loss function, maybe it looks something like this. Then we start with a value maybe here, and we compute a gradient. It's going to point this direction, so we're going to take a step in the negative gradient direction, a little step, and how large this step is determined by the learning rate. And so you repeat this process over and over again and hopefully at some point you get to your minimum. So that's the entire idea of this gradient descent algorithm. Okay, let's now define a learning rate. Just take this one because I know it works later on. And this is now our entire function. So let's see what this does. Okay, so our goal is to update our guesses. All right, so this is sort of what we want to get. So this is what we want to update. For this, we then compute the predictions based on our current guesses. We also compute the loss, but we don't actually need this. We just want to print this out to monitor if the loss is actually going down. That's always a good idea because otherwise you don't know what you're doing. We then compute the gradients. So these are these two values here, right? So there's the gradient of L with respect to B, and the gradient of L with respect to A. And you have our true values here and our predicted Y values. And now we're updating our A's and B's. We go in minus the gradient direction with a learning rate step, okay? So this is the entire algorithm. Then we iterate over this process over and over again, and hopefully at the end we'll converge to a certain solution. Okay. Right. I wrote a little function here to animate this. So this is now going to take 20 times 100 steps, and we can see what happens. It's going to take a little while. I messed up. 1 second. This will look much nicer. Okay. So what you can see here is, first of all, we're printing out the loss, so it's going down as we take more and more steps. What you can also see is that we get a better and better fit of our line. So this is just a line that I draw with our current A guess and B guess. And you can see we get a better and better fit. So this algorithm works, right? So this is kind of cool. So we have now an algorithm where we just figure out, we have some training data, and we figure out what the parameters are. Okay. So this is linear regression. It's nothing new, but maybe some insight will be gained, because neural networks are really not that different. And the first thing we can do is we can think of linear regression in terms of a graph. So really what it is you have some x here. You want to predict a y. You have a connection here with some weight a. And then you also have a bias term. That's our intercept, right? So we can simply draw this sort of as we have a 1 here, a connection here with b, and then y equals ax plus b1, right? So y is a weighted sum of all the nodes. So we're going to think of these as nodes now in the previous layer, right? Okay, so this is basically a very simple, it's not a neural network because there's no nonlinearity, but it's a network. This is a computation graph. And so this is how you typically think of operations if you do neural network programming. And this is also how Keras thinks of these computations. And Keras is a high-level deep learning library. So it allows you to write neural network code in a few lines. And we're going to do the same thing that we just did explicitly in Python now with Keras. Maybe let me ask here, is everybody still on board with what we're doing? Sounds good? All right, and let's move on. So now first we are going to import some Keras modules, and we're using TensorFlow in the backend. So TensorFlow is sort of the low-level deep learning library. You would need to write a lot of code to get what we do now, but with Keras it allows us to do the same thing in very little code.
TensorFlow is actually designed for this image processing, right?
Well, you can do anything. It's a pretty general purpose. You can do all sorts of, well, basically what it is, you can design computation graphs with TensorFlow, and you can differentiate backwards. So that's the key thing, but that's for all the image processing, for all the image neural networks, that's exactly what you need. So yeah, it's most commonly used for image processing or natural language processing. But basically what it does, it designs a computation graph. It allows you to do the same thing on the GPU, and you can differentiate backwards, which we need to compute the gradients for the neural network. But Keras basically uses the same thing in the background. It just like is a nice wrapper around it, so we don't have to write ugly TensorFlow code.
So then you have a question, would the animation you showed, would that still allow for?
So actually, what you see is that it never actually converges. And I think this is because the learning rate is too large. So if you use a really large learning rate, why don't we just try it out? I mean, that's the beauty of these notebooks, right? So I guarantee you that it doesn't work if they set the learning rate way too large. Let's just start with some values again. Well, let's see what happens. I don't know. Still works, even better. Okay, this doesn't seem to work so well. Yeah, so at some point it doesn't work anymore, right? Choosing the right learning rate is sort of trial and error. There is no like formula to do it. You try something, you try a larger one, and it still works. So you want it, of course, to be as large as possible because
it's ridiculous to expect that it will work for every because it's a fixed point problem.
Yeah, no, it's different for every problem. Yeah, but even for a single problem, there is not a rule to choose your learning rate. No. You just pick a value, you pick a bigger value because that would give you faster convergence. And at some point, it doesn't work anymore, so you pick a smaller value again.
There's a convergence radius. Choose the right one for your problem.
You can also start with a large learning rate and get down to smaller learning rates if you want faster convergence at the beginning. So, right, bit of trial and error. Okay, so now let's build the same thing that we just did. So basically, this computation graph in Keras. So in Keras, there's two ways to define a neural network. And we're going to look at the easier way, the sequential way. So in the sequential neural network, you basically have one operation after the other. There's a different way where you can be more flexible, but we don't need this for today. So we're going to define a model by calling sequential. And then you put all the layers of the neural network in a list. Okay? Now, we only have one layer. We only have one operation. And this is a dense layer. So a layer where all of the nodes in one layer are connected to all of the nodes in the next layer in Keras is called a dense layer. You'll also hear the term fully connected layer thrown around. Okay, so that's your basic neural network operation from one layer to the next. Okay, so let's see what these numbers mean now. So this says units, okay? And what this means is this is the number of output units, okay? And so we have one value that we want to predict, so it's 1. And then for the first layer in our Keras network, we also need to define the input shape. And it's also 1, because Keras assumes that you have a bias term, right? So we only have one input layer. And you can actually see, if we look at the documentation, it has use bias equals true. So it automatically adds this bias term. So in that way, we only have one input and one output. Okay? And that's basically it. You need to put a comma here. If you're interested in why, ask me later, but for now, just do it. Okay, so let's define the model. And what we can do now actually is we can check out the model. So if you've defined a model, you can do model.summary. And it's going to say it has one layer, it's a dense layer. And the parameter, the number of parameters is 2, right? Because we have A and B. So it's one parameter for the weight between X and Y, and then it's one bias parameter. So this is exactly what we want. Now we need to compile the model. Basically what this means is we tell it what optimizer to use. We're going to use stochastic gradient descent. I'll explain the difference between stochastic gradient descent and gradient descent in a second. We're going to choose a learning rate for it, for this optimizer, and we're just going to choose a loss function, right? So again, we can look here, we have optimizer and loss, and we're going to choose the mean squared error loss.
This has nothing to do with the function you find with it. Is that true?
Yeah.
So this MSA is just...
It's your loss function.
You choose the same name, but this is a fixed term for the library, MSE.
Yeah, there's some predefined functions, for example, the mean squared error, yeah, some other common errors. You could also define your own function.
In the same way, because it's what it is.
Yeah, so you can go to the Keras documentation, and there's a number of predefined loss functions that you can just type the name in. Yeah. Otherwise, you need to define your own function.
But that's what we can. We can define your own.
Yeah.
Okay.
Yeah. Right, and so we compiled the model now, and we need to do this. And now we're going to fit the model. So we're going to pass it our training data, our x's and our corresponding true y's. And now there's a lot of like terminology that you're going to have to get familiar with. Batch size and epochs and all this stuff. So what does that mean? So if you have your training data, so you have some x's and you have some corresponding y's. What we did so far is we used all of this data to compute our loss. So we looked at all of the training data at once, okay? Now, this is easy for us because we had like 50 examples, but sometimes you have too many examples to really do that, right? It doesn't fit into RAM, or it just takes too long to compute. And so what you usually do is you look at little pieces at a time, right? And you shuffle around these pieces randomly. And so you compute a little gradient update with this piece, and then this piece, and then this piece. And how many elements are in there is the batch size, right? So this is, batch sizes are typically like, it could be like 128. That would be, you look at 128 training samples at a time, compute a gradient update, and then you go to the next one. And because you shuffle them around randomly, it's called stochastic gradient descent, right? The algorithm. Now, once you've gone through all of your batches, you've completed an epoch. So an epoch is when you've looked at all of your training data once. And so normally you do several epochs, and then you shuffle again and you go through all of them again in a stochastic manner. And so this is what these things here, you define the batch size, and because we don't really want to, in this example, don't want to do stochastic gradient descent, we're going to look at all the samples at once. We're going to pass it the number of our training samples. So this is 50. So the batch size is equal to our entire training data size. So it's just regular gradient descent. And we're going to say do this 1,000 times. And it's going to do this now. And it's done. That's the great thing about using easy data. And now we can plot the loss, right? So this is the function that we want to minimize, and we can monitor that it actually went down. And it did go down. And we can in the end also look at the values that we got for the two parameters. And we see it's 2 and approximately 4. So we learned the parameters as well. Now we used Keras. Okay, so that was basically how to do the same thing in Keras. And this is going to allow us now to use Keras to do something a little more complex and code up an actual neural network. So again, let's take a little break here if anybody has questions. Yep.
You said you use all the data at one go for the line at one.
Yeah.
How do you get 1,000 epochs then? I mean, you only have one, you don't randomly.
No, so, okay. So an epoch is basically, it's when you look at all your data once, right? So what we do is we look at all our data, we do a little gradient, we compute the predictions of our current model, right? With our current A's and B's that we guess.
Are they like iterations?
Yeah, they're iterations, right? So in this context, because we use a batch size that's equal to our entire training data size, epoch is the same as an iteration in our context. Normally an epoch is when you've completed all of the batches in your training data. So when you went batch by batch through your entire training data sets, when you finished at the end, when you've seen all the training data, you start again. That's one epoch, and then you start again with the second epoch, and you randomly shuffle in between. Another question? Yeah? Uh-huh.
Compensation of errors. I mean, when you talk about the bias, one, etc.
So,
I'm not clear if it's.
yeah, so I mean, in the network that I presented yesterday, we didn't have 2 parameters, we had 500,000 parameters. So, really, it's not really a compensation of error. You don't really know what's going on in between. It's just going to find the best parameters to get the best fit to the training data. How or what's happening in between, you don't really know.
Okay, so that's the best collection of parameters that gives you the best estimate, but you don't have the detail of the.
No, you don't know what's going on between. Yeah, so it's sort of a black box. I don't really like, a lot of people always say neural networks are black boxes. That's not entirely true because you can interpret the output and the input. You're not going to be able to interpret each parameter in the neural network, but there's methods to actually look into the neural network. Okay. All right, so that was boring. Let's go into something a little more interesting, okay? We're going to do the absolute standard task in neural networks now, and that's recognizing handwritten digits. So there's this famous data set, it's called MNIST. Don't ask me what it stands for. Some American institution, I think. And they have collected this data set of handwritten digits here. It's grayscale images, 28 by 28 pixels of digits with labels. And our task is now to look at the images and predict what number it is. Okay. So let me say something briefly about neural network libraries. So we're using Keras now. Keras is sort of the simplest neural network library. And Keras can use different what's called backends, right? So this is what actually does the computation. It basically just is a wrapper around these. The most common one is TensorFlow. And TensorFlow is probably also the library that most of you have heard of. And TensorFlow is Google's library. You can do anything with TensorFlow, but TensorFlow code is sort of ugly because it sort of fits into Google's coding environment. So they define all of their own terminology and everything. And to write a simple neural network, you have to do a lot of, just ugly stuff. It's totally fine. And there's a lot of support out there. But there's another low-level alternative now, developed by, not directly, but indirectly by Facebook, I think. It's called PyTorch. PyTorch is just as flexible as TensorFlow, but it's more Pythonic, right? It's like it uses classes for everything, and it's you can write nicer code with it. So that's just a bit of an overview. So let me clear all my output. Risky. All right, let's start again. Okay, so let's import this now. If you want your code to be reproducible and use anything random in it, you want to set the random seed. So this is what I've done here. And now we're going to, first of all, the basic thing, if you get a new problem in machine learning, is you have to look at the data, right? And you have to understand what's going on in the data, and you're going to have to do some pre-processing. So Keras already comes with this data set. So we can just do Keras datasets, MNIST load data, and if you do this the first time, it's going to download the data from the internet. I've already done this. And then the first thing that you should always do if you get like something is look at what shape it is. So these are NumPy arrays, right? And so we want to understand what shape are they in. Okay, so also what are all these different things that we're actually getting out of this function call. All right, so we get 4 things. The first is an X-train, and it has dimension 60,000 by 28 by 28. You know, we already know sort of 28 by 28 is our image dimension, so 60,000 must be the number of images that we have. We have a Y-train, that's just 60,000, so that's probably going to be our labels. And then we also have an X-test and then Y-test with 10,000 images in it. And so what is that? What is it? Why is there a different training set and a test set? And you'll hear people talking about a validation set. So these are really important concepts in machine learning. So I want to illustrate this really quick. So your training set is basically all the data that your algorithm, whatever that may be, sees during training and uses to optimize its parameters. Okay? Now, you can do this, and you can find a great algorithm that fits really well to your training data. The best algorithm would actually be to just memorize your training data, right? But that's kind of useless, because what you really want from a machine learning algorithm is you want to get predictions for new data. That's why you use machine learning. And so you can have a really great algorithm that fits to your training data well, but doesn't generalize to your validation set. So to other data. So that's why you want to have a validation set. So a validation set is some part of data that you set aside, that you do not use during training, and that you then use to test how good your algorithm is on some new data that it hasn't seen during training. So that's absolutely crucial. And the process where you basically memorize your training data and you don't generalize well to new data is called overfitting as well. So that's something you'll hear people talk about a lot, is overfitting. Okay, so that's great. And so for your validation data set, you also know what the outputs should be, and you can compute the score on that and see, well, how good is the score on that. Now, if you're a really good machine learning practitioner, which we're not going to be, but if you're a really good machine learning practitioner, and particularly if you do something which actually matters, what can happen is that you build 100 models, right? Like you work on a problem, you try out a wide variety of parameters for your different models and so on, and you check every time, well, how good is it on the validation set? And then you choose the one that's best on your validation set. But of course, a good skill on your validation set is also not what you actually want. What you actually want is you want to have good predictions on a data set that you don't already have. So if you want to be a really good machine learning practitioner, you set aside a third data set, which is typically called a test set, which you never look at, even if you evaluate your model during your development process, and you only look at right at the end to test, well, does it give me reasonable outputs or not? Now, we're not going to use this, and for most problems, it's not that important. But if you ever do something that actually matters, so if you have a machine learning algorithm that makes decisions that people actually really care about, or that make important decisions, then you want to do this. So these are just terms that you will hear. We're going to just treat validation set and test set interchangeably for this. For us, it doesn't matter. All right. So we got some data. It's image data. So let's plot some images. Okay. So here we have some images with the real labels. So they should all be correct. Fine. Looks good. All right. So now we're going to have to do some pre-processing, okay? And the first thing is, these image data sets usually come in RGB or here in just grayscale. And so they have, if we just look at the first one, they have values between 0 and 254 usually. This is what you can see here. So this is what the image actually is. And for gradient descent to work well, all your inputs, so these in this case would be all the pixels of our image, should be about the same range. Now, they already are, but it can happen. For example, what I presented yesterday, we put into the neural network a temperature, we put into the humidity. They have widely different scales. So what happens if you do this is that you end up, so imagine, now of course we're in multi-dimensional space, so we imagine we still have sort of this structure. what happens is that your loss surface, so this is sort of what you want to minimize, will look something like this. So it's really skewed, and that's really inefficient, because then your gradient descent algorithm will do something like this, and it might never converge, or it might be very slow. And this is actually a problem. I've many times forgotten to normalize my data, and it just doesn't work. If the inputs are too wildly different, it doesn't work. Now in our case here, it doesn't matter, because all of the images are going to be between 0 and 255, but it's still common practice to normalize them to a range that's approximately between 0 and 1. The exact details don't matter. And so we're going to just define a normalized function where we divide all of the values by 255. A very common way of normalizing when you don't really know what the range is to subtract the mean and divide by the standard deviation. But one important thing to remember here is that if you do this, you have to normalize both the training data and the test data, or your validation data set. And you have to use the same values for those, right? Because if you, for example, use the mean of the training data to normalize the training data, and the mean of the test data to normalize the test data, your algorithm will not be able to cope with this. So you need to use the same values. That's very important. But in our case, it's easy. We just divide everything by 255. So we can then look at the data, and it's going to be some numbers between 0 and 1 now. And so I just plotted an excerpt here. So these are the numbers, and these are the representations if we plot it as an image. So really an image is just a bunch of numbers. All right, we're going to do something pretty dumb now, okay? So an image is a 2D structured array. We're going to throw away the structure. We're going to flatten out the image. So we're going to go from something, we have a 3 by 3 image. It has some structure. We're going to simply take the image and flatten it out, right? So to do one long vector. We're going to do this because it's easier at the beginning, but we're going to later learn how to do this properly. But for now, this is fine, and we can simply use NumPy's reshape function, and we want to retain the first dimension, which is our number of images, but we want to flatten out the other two dimensions. We're going to apply this to the train and test set, and we now see that we have arrays where we have 60,000 images, and then one vector with 284 elements. That's 28 by 28. Mm-hmm. This is just the first image from our training data set. Yeah, so you can see this is our training data set, and I just indexed into this. This is the first image. So Python uses 0 indexing, right? So 0 is the first. And I just sliced into it and just picked some random values. They're 3 by 3 values. Now, if you don't, I'm going through this pretty fast. If you don't follow all of this, that's not that bad. As long as you get the overall concept, that's fine, because you're going to have these notebooks, and you can go through them later on your own time and really try to understand, what did I actually do here? What is this imshow function? What arguments does it take? Ask me, ask Google. Google is probably better than me. And well, it certainly knows more. Yeah, probably is. Okay. All right, so now we can plot our flattened array. So remember, we flattened the array, and wait, let me out of there. And so we now have one long vector. So that's our image that's just been totally mishandled. In any case, so what we're dealing with here is a classification problem, right? So there's basically two types of big supervised learning problems. One is classification, where we want to predict, is this type? Is it this type? Is it this type? And then the other thing is a regression problem, right? Where we want to predict a real value, like, well, what's the subgrid heating going to be? Or some other less interesting problem. There's only less interesting problems, no. And so if we look at our y's, so this is what we want to predict, we can see that it's the numbers, right? So if we go back up, the first is a 5, 0, 4. That's exactly what it says in our training data. Now, this is, if we could of course set up a neural network that just predicts values between 0 and 10, but that doesn't really make sense in our case because 1 and 2 are not closer to each other than 1 and 7, right? So we don't really, so if we treat it as a regression problem, it doesn't really make sense. So we're going to do something that's called one-hot encoding.
There's no matrix. Like you cannot compute the difference between the two categories, right? That's why regression doesn't make sense.
Yeah, it makes no sense. Stupid for me to even mention it. It's dumb. But we're going to do something semi-clever with it. We're going to do one-hot encoding. So we have our array where we, let's say, have 5. And so we know that we have 10 categories, right? So we're going to convert this 5 into a vector with 10 elements, and all of these elements are going to be 0. I need to count. 1, 2, 3. Except for the 5th element, which is going to be 1. So this is what we want to predict now. So this is a vector with 10 elements, and at the position where we have a 5, we're going to have 1. So this is what we want to predict. And it doesn't need to be a 5. This could be cars, trains, birds, if you would, something like if you do an image classification algorithm. So you simply convert your numbers into a one-hot encoded array. Yeah, if you're mathematically inclined. Okay, and so what we predict then, I'll get to this later. Let's just first do this step. Okay, so we've seen this is what our training data looks like, and we are going to use, for this one-hot encoding, we're going to use a function that's already provided to us by Keras. We could, of course, code this up ourselves, but if we use this two-categorical function, it's going to do this one-hot encoding. So let's see. Converts a class vector integers to a binary class matrix. Sounds about right. And so we can see now, so our old training data had these numbers in it, these integers, 4, 0, 5, and now our one-hot encoded training data is a bunch of vectors that have ones at the position where we had our integer. So here we have it at the first position for the 0. Here we have it at the, well, 5th position for 1. So you get the concept, right? Okay. Now we sort of pre-processed our data. We have normalized our input data. We have one-hot encoded our output data for our classification problem. And we're going to train a simple linear network now. So we're going to train a network that takes our flattened image as an input. So that's our input array. So it has 700, I think it was 48, or was it 84? Doesn't matter. Input values. And it produces as an output a vector with 10 elements for each of these classes. And what this now represents is the probability that it's one of these classes. So it's going to produce a vector with 10 elements, and it's for each of the elements going to tell us this is the probability. Okay. So again, we use our sequential model. We're going to use, this is one layer, one matrix operation. We have 10 outputs. We have 784 inputs. And then it says something here, activation equals softmax. So maybe you remember me talking yesterday about activation functions. Activation function is a nonlinear function that's applied to all the output nodes, or it can also be a layer operation of a certain layer. And so we use something called a softmax. The softmax is defined here. Now, the reason why you don't just want to use a linear layer is because we know something about what the outputs should be. We know that they should be probabilities, so we know that they should add up to 1. We know that each one of these should be between 0 and 1. And we also know for our classification problem that one of them one of the probabilities should be much higher than all the other probabilities, because it's only ever one of these classes. And so this is exactly, these factors are exactly what the softmax function reinforces. So this is what it is. It takes the exponential of all the output values, so that's our 10-dimensional vector. And so what this does, if we just have a random, oh sorry, I need to define this. If you just choose some values, if you take the exponential, it's going to make the larger values a lot larger, right? So here we have values that are approximately the same range. If we take the exponential of this, the larger values are going to be a lot larger. That sort of reinforces that we know that one probability has to be much higher than the other ones. And then if we divide by the sum of this vector, we're going to normalize it to be between 0 and 1. And so we get something that sums up to 1. Each of the individual values are between 0 and 1, and one of them is much higher than the other ones. So this is just one function that's very commonly used. It's probably not the only one that you can use, but that's one that we're going to use for our classification problem. Okay, so that's sort of the first change that we need to apply to our linear problem. The next one is, how do we judge how good a prediction is? So again, we could use the mean squared error as we did with our linear regression problem, but it's probably not the best function. And so actually, what you typically use for this type of problem is something called the categorical cross entropy. And so it's plotted here. So it's basically, so these are your true predictions. So it's YT. So this is going to be either 0 or 1. So this is for each of the 10 classes. So you see C is the 10 classes that you have. And so you sum over those. And so YT is going to be either 0. So you have, if it's not that value, you have 0 contribution to the loss function, or it's going to be 1 if it's the actual number that you want to predict. And then you look at the logarithm of your prediction. And so the closer you are to 1, the lower, because we have a minus here, the lower your error is going to be. So again, don't worry too much about this. This is just a typical loss function for this sort of classification problem. And again, this is something that's predefined in Keras. We can just write categorical cross entropy, and Keras knows what to do. Also, we're going to compile our model again. And the first thing, remember, is the optimizer. And before we had stochastic gradient descent as our optimizer, we're going to use something called ADAM now. ADAM is a sort of an improved version of stochastic gradient descent, but it's basically the same thing. And also we can pass along another metric, so that's just for our interpretation, because we're going to minimize this categorical cross entropy, but that doesn't really mean anything to me. If this, it's just a number. If it goes down, it's great, but I don't know what it means. But what we can actually do is we can look at the accuracy. How many images did we classify correctly? Or what percentage of images?
So why use this categorical cross entropy and not MSD like we did for the linear problem? Because the cross entropy will not take any error for the prediction is significantly larger than 0 for a wrong number, but only when it's smaller than 1 for the right one, right? As it's defined, it will only...
Yeah, you're right.
Yeah. So why
I agree with you. I don't have an answer for you. I know that everybody uses this for this kind of problem, so I hope that somebody thought about this at some point. But it's a good question, and I don't know the answer for it. So yeah, I don't know. I'll Google it later. Maybe you have a satisfying answer.
Can I give an answer?
Yeah, sure.
So the softmax function, if you have a 0, let's say you see a figure and it has a 9, but you estimated a 0 probability of having 9, your punishment for that is infinite punishment. It's really try not to kind of more spread the probabilities, because look at the logarithm function. If you estimate something at 0 probability but you are wrong, your loss for that is infinite. So it's kind of more, it has a tendency more to split a bit more the probabilities you get, while mean squared error, the maximum punishment you can have is 1. Because let's say it's 9, but you predict the 0 probability of having 9, your loss function will accumulate and not just 1. So this has a more tendency to this split more your probability.
So missing the right answer has a much higher error than the error for having the wrong answer.
In fact, I mean, look at how the loss looks like. It's like an entropy. So, as we said, I mean, generally do what works best. But this is very common entropy. It's very common used in machine learning. So just in the end, it works better. But I think the underlying reason is that it makes you a bit more, tends to make you a bit more uncertain. The mean squared error is much more linear, in a sense, linear accumulation of errors, and this is much less linear than mean squared error.
Because it's a category, because it's about categories, it doesn't make sense to compute differences you base other computations on. This is a yes/no decision, which is perfect for choosing the right category. But just because we're expressing all this in numbers, because our machines can compute in numbers, it looks like it has something to do with 5, 1, or something. But the mean square error is like it's just our imagination that we're computing with numbers, but actually we don't.
No, but you could put in mean squared error the probability, then you won't.
Well, maybe we'll postpone this discussion to the end. Interesting stuff to think about. All right, so we compiled our model now with all of the hopefully right parameters, and we can then look at the summary, and we see that we have about 7,000 parameters. So that's a connection between all of our 784 input values and the 10 output values, plus the bias terms for the 10 output values. And then let's fit it. So we pass in our flattened training data set, our one-hot encoded labels, and now we're going to do actual stochastic gradient descent. We're going to say we're going to choose a batch size of 512. That's a common value. You can play around with this. You might get better values. We're going to do this for 10 epochs, and after each epoch we're going to test how good our predictions are on the validation data set. So let's run this now. And it's running. That's great. And so you can see it's going through the epochs. It's pretty fast. That's nice. We can look at the loss. It's going down. Great. We can look at the accuracy. It's going up. And that's for the training data set. And it's also printing out the same thing for the validation data set. So the validation loss. And we can see that's also going down. And the accuracy is also going up. And in the end, we could train it more and we might get a little better, but not much. And we can see that we get an accuracy on the validation data set of about 92%. Pretty good. Let's now look at some predictions. So we have a model now that's trained. We can now call the .predict function on our test data set. Now what you can see is that the predictions are 10 are vectors with 10 elements, and each of them is sort of the probability. And you can see if you look, where's my mouse gone? One of them is much higher than all the other ones. So all the other ones are really small. So the sort of our softmax in combination with the cross entropy is sort of enforced that one is much higher than the others. Well, we don't want probabilities, we want like actual predictions, so we're gonna call the NumPy argmax function, which is just gonna pick the one with the highest number, and so it's gonna end up bringing something like this. Oops, 721. We can plot this now, and we can check how well we did. So these are now our predictions, right? So these all look right, except for this one, which is probably a 5, I would think. But it's predicted a 6. Understandable though. Okay. So that's always also a really good test. Like check out the predictions. Like see what the neural network gets wrong, and we see that here it's not too bad. It's getting the ones wrong that are difficult for us to discern as well. All right.
I don't understand why the prediction is correct, although we linearize the image.
So
because the image is just the way we look at it, but it's represented as a matrix or a list of vectors, and the shape of what you see is also like there if you have all the pixel lines in one long line. It's just you don't visualize it, but the computer does.
Yeah, so the reason is that kind of the images are somewhat evenly spaced.
Yeah, I mean they're all sort of centered. So what it's learned is sort of to know, well, if there's a high number here and a high number here and a high number here, and the combination of those, then it's most likely going to be a 0 or a 7 in this case, right? So it's simply like looked at these individual pixel values and from the training data set figured out if these are high in combination with these, it's probably going to be this number. And of course, this is a very constrained problem. All of these numbers are sort of, you know, like you can see these ones are always something in the same position, these 4s. So it's sort of just learned to associate individual pixel values with a probability that it's a certain number.
All right. So it just works because the images are so nice and the lines are...
In this linear and dumb neural network that we coded up, it only works because the images are so nice.
Okay.
Yeah.
Could you run sort of the network in reverse to find archetypical interpretation for each of the numbers?
There's ways to do it, but talk to me about it afterwards.
Okay, but just
yeah, there's neural networks that create images. So yeah, you can run something like this, but it's a little more complicated. Okay. All right, now let's finally do a neural network, right? So again, we've just done a linear network. It's boring. So what is the difference between a neural network and a linear network is that it has hidden layers in between. So in between this step and this step, we now have another layer where all of these nodes are connected to all of these nodes and with a certain number of nodes. And the difference is now that for this hidden layer, we use some sort of nonlinear activation function. So after you do the matrix multiplication here, each of these values are passed through a nonlinear function. And the function that we're going to use is called a rectified linear unit. And a rectified linear unit looks something like this. So it simply sets all the negative values to 0. You could also write max 0 input. Now, this is a pretty simple nonlinear function, but as I mentioned yesterday, it turns out that if you combine a lot of them, you can actually approximate complex nonlinear functions. And again, if you don't believe me, there's this awesome link here. This is an online book on neural networks. It's a visual proof that neural nets can learn any function. And there's like some interactive widgets down there where you can play around with these values. And for some reason, on my surface here, there's supposed to be a blue line, but it doesn't get displayed. And I don't know why, so I can show it to you, but feel free to play around it on your own time. Okay. But in any case, let's just assume that it works. And so now we're going to define our model with sequential, but now we have 2 elements in this list. The first is a dense layer that takes the input vector and produces sort of this hidden layer. So that's this one. And we can choose how many nodes we want in this hidden layer. Just, yeah, so it shouldn't be too different from the input shape, but it really, there's no like rule for doing this. It's just people have found things that work. And so we're going to use one that I know works because I've tried it out, and it's about 256 nodes. But it would work well for the double number of nodes or less as well. Of course, the more nodes you have in that, the more parameters you have, so it gives you more computing power, but it also network's going to be larger and it's more prone to overfitting. And we're going to say for this layer, we want to use the ReLU activation function. And then we're going to go from the next step, so from our hidden layer to the output layer, and that's similar to before. So we have our 10 outputs and we have the softmax activation. And you only need to specify the input shape for the first layer. The next layers are going to figure it out on their own. So this layer knows that the previous layer has this many nodes, and so you don't need to pass it to it. Okay, so we're going to compile it in the same way as before. We're going to look at the summary. This one has 200,000 parameters now, so it gets large pretty quick. And we're going to do the same fitting, but it's still a problem that runs reasonably quickly on my laptop here. So let's just do see how it does. The loss is going down. We can already see we're getting better values. So this added nonlinearity really gave us some extra computing power. That's great. Almost done here.
One question.
Mm-hmm.
So the redo function effectively throws away those connections in the graph that don't have any meaning to the problem.
That's not really what it does. It sort of, it looks at each one of these. So you do the weighted averages, right, for this, and then it looks at each of these values and it says, well, if it's below 0, we're gonna set it to 0, right? So it's just a simple nonlinearity. The neural network can then figure out, well, how do I need to arrange this in sort of these connections to get some sort of nonlinearity in there. I don't know really how to explain it. I would really suggest you check out this link that I provided, because it's going to give you a visual understanding of what this actually is. But I don't think anybody really knows why it works or what's going on.
Until 2 years ago, zero was not in use almost. It's like a matter of fashion. 2 years ago, people used to use different functions.
Yeah, so
that proved itself to be better than others.
So, like, what people used for a long time was sigmoid functions, or something that looks like this. Works just as well. People have found that this works a little bit better. I mean, what people really use now, I think mostly is called a leaky ReLU. That looks something like this. Let's try it in this crazy pen, and it also has a slope here, but a reduced slope. So it's just a lot of trial and error, really. All right. So this is done, and we got up to about 97% accuracy, and we can see a little bit of overfitting here. So in the training data set, we got over 98, and on the validation data set, we got over 97. So that's a little bit of this overfitting that I talked about before. But hey, that's pretty good. Now you can stack many of these hidden layers on top of each other. So you can squeeze in more of these hidden layers in there and more, and then you have a deep neural network, and then you're doing deep learning. So we're already doing deep learning. Fantastic. In Keras, that's super easy. Forget about this dropout business for once. You just stack these dense layers on top of each other. So now we have 3 dense layers with 256 nodes, and then the final layer is again the one with the 10 outputs. And for each of one, we use the ReLU activation function. Okay, so we already saw that so let's just see really quick how many parameters we have. We have 330,000 parameters. So we already saw a little bit of overfitting for this one, right? And the more parameters you add, the more you're going to run into this problem of overfitting. Now, the really simplest solution to prevent the neural network to specify itself too much to your training data set is something called dropout. And again, this is a very empirical thing. So what is dropout? Let's draw another nice neural network. So let's draw one with 4 and 3, and you have a connection between all of these. Okay, so this is like a layer operation for a neural network. What dropout does is it says, during training, I'm going to set a certain percentage, so let's say 25% of these connections to 0. So I'm just going to X them out randomly. Every time we pass a new batch of data through, we're going to randomly set some of these to 0. And what this does is that the neural network has to sort of like, it cannot like specifically learn like this function, because it cannot rely on there being this connection in the next training step. So it sort of is a little bit more generalizable. again, this probably, if you're mathematically inclined, sounds terrible to you, but it turns out it works really well, right? So we're going to use it. We're not going to complain.
And it's different for each epoch.
It's different for each batch.
It's different, yes, it's different for each batch.
Yeah, and so we see we can pass a probability in there, and so it shows 0.25, so 25%, 25% between these two layers, 50% for the later layers. People have found out that it's better to use more dropout for later layers. And we're going to run it, and you can see it takes a few seconds now. But if everything goes according to plan, it's going to give us a better fit later on. And so we now built a deep neural network. But while this is running out, I already want to show you the final thing that we're going to do. And that's, in the beginning, we flattened out our images. And that's really kind of a dumb idea, because images really are, the structure, the 2D structure of the image is really important. And to exploit the 2D structure, we're going to use a convolutional neural network now. So you probably have heard of these CNNs. And basically, what convolutional neural network does is, instead of using these fully connected layers, it learns kernels, right? Image kernels or convolutions. And so what's an image kernel? So an image kernel is a matrix. So this is a 3x3 matrix. It could be a 5x5 matrix, whatever. And it's a matrix that has some numbers in it, right? And so image kernels have been used in traditional computer vision for a long time, because you can define certain image kernels. For example, this one, which is called a bottom Sobel, apparently. And what it does, you can see, it highlights the bottom edges of an image, right? So if we take the top Sobel, it highlights the top images. And that's just because, I should explain what it really is. So what you do is you go over each image, over each pixel in the original image, and you multiply each 3x3 square with the numbers in that kernel, and then you add them up, and that's your output, and you get another picture that's one smaller, because in the edge you don't really know what to do, or it matters a little how do you define it. But anyway, depending on the way you define this, you find different features in an image. Now, in a convolutional neural network, what you do is, rather than specifying this kernel, this matrix, you learn what the best kernel would be to give you the best fit to your training data set, right? So you end up with a bunch of these kernels to give you the best fit to your training data set. Where are we? Let's have a look. We got about to 98% with our deep neural networks for the training data set, and you can see that the overfitting isn't quite as bad as we had before, and that's because we used dropout. Okay. All right, so we want to use these convolutions now, and it's actually really easy. So the first thing we have to remember, we shouldn't use the flattened out images now, of course. So we use the full images, and they have the following dimension. So we have 60,000 samples and 28 by 28. And so again, we're going to build a neural network. You're going to use the sequential neural network. But now, instead of a dense layer, we have a 2D convolution layer. Okay, so first of all, we're going to have to specify for our first layer the input shape. It's going to be 28 by 28 by 1. And this 1 means that we have one channel. So we could use the same function for a 3 channel image, so for a color image, and then this would be a 3. But you need to specify that it's only one channel. That's just how this function works. It expects a input where you have the last dimension is the number of channels. And then we're going to define 32 different kernels, right? And the kernel size is 5. So that's, if we go back to this one, this is a kernel size 3. We're going to have a kernel size 5. Oops, that's not how this works. And stride 2 means This would be a stride 1, so you go over every pixel. Stride 2 means you jump over one. You take every second pixel in your original image and compute the kernel for that. So again, if this is a little confusing to you, I'm sorry.
So still you have an overlap of 1 pixel.
You have an overlap, yeah, right, because you have kernel size 5. Okay, but so yeah, for now, let's just assume that it works. We have the value activation function again, and then in the next convolutional step, we're going to use 64 kernels and then 128 kernels. And because we use stride 2, the images are going to get smaller and smaller as we go down. What did I do? Let's just look at the summary. So our original images had size 28 by 28 by 1, right? And after the first convolutional layer, this always specifies none, it says, because it doesn't yet know how many images you're going to feed into it. So that would be the batch size, but that's just how many images. And after the first convolution, because we use stride 2, we have now a 14 by 14 image or matrix with 32 channels, sort of. And then we're going to do the same step again. We're going to reduce the size of the image and again. And so in the end, we end up with a 4 by 4 by 128 matrix, which we're then going to flatten out. Okay? Don't worry too much about it. It works. And then we have our regular dense layer that we had before. And we can see it has 100,000 parameters, so it's less parameters than our fully connected network. That's one of the big advantages of these convolutional networks. They allow you to do more with less parameters. We're going to compile it in the same way. And this is actually going to take a while to run. So I'm going to just start this now and explain some things while this is running. And this might actually take a long while, but I can already promise you it's going to get a better fit than the previous data set. Okay, so the first thing we need to remember is that it expects now, so our original training data, as I already said, has 28 by 28, but it expects something that has the number of dimensions as the last dimension. So we can just add on a dimension 1. We can use this with the reshape function in the end. And also, you know, this already takes quite a long time on the laptop. If you want to do serious machine learning, you probably should look into getting access to a GPU, right? These are your graphical processing units on a computer, and unfortunately not every GPU works for deep learning. It needs to be an NVIDIA GPU, it needs to be a specific NVIDIA GPU, but most of you, I'm assuming here at the Max-Planck-Institute, you also have some access to these GPUs. It's going to speed up these computations factor 100 or something like this, because GPUs are really good at one thing. They're really good at matrix multiplications, and that's the only thing we're really doing, matrix multiplications, right? So that's one thing. And there's also cloud options for GPUs at the moment that are pretty cheap or even free. So yeah, that's absolutely necessary if you deal with large amounts of data or more complex networks as our convolutional neural network here.
Where do we get free computational resources?
Where? So there's one resource at the moment. Google Colab allows you to create a notebook in their cloud server or whatnot, and you can rent a GPU for free for 12 hours at a time. So you could do the same thing that we just did using their Colab notebooks. I think it's basically the same thing as a Jupyter notebook. And you can say use GPU or whatever, and you can use it for 12 hours at a time for free. There's also other cloud options, but you can also check whether your local server has some GPUs lying around. It's pretty easy to use as well. The only thing you need to do differently is, remember we did this conda install. If you use conda, you did this conda install keras. You would do conda install keras minus GPU, and it would install all the necessary things to use a GPU. So it's really easy now to use that. We can see we're already pretty good here, and it's just going to get better. but we're not going to wait now. That's basically the end of the tutorial part. So what I'm going to do now is I'm going to sort of introduce the task that I have prepared for you, but also feel free to go. I will not be offended if you say, I've had enough, I don't want to actually code anything myself. That's totally fine. And so I think, so I'll be here to help you with this. So I would suggest that you work in like groups of 2 or 3, then you can help each other. So if you're pretty new to Python and you were like, wow, this is already like really challenging, what I would suggest is, why don't you try to go through this notebook that we just did, this MNIST notebook again, oops, and just open up a new notebook and try to do the same thing that we just did and write it down yourself. So what's really important when you learn something, when you want to learn something, is that you don't just go through this notebook and click like Shift Enter and go through all the cells, because that's really not, you don't know, you don't learn anything. What's more useful is if you open up a new notebook, and even if you cheat and look at the old notebook and just copy it down, the act of writing helps you to learn and understand what's going on. So that's one option. If you're like, that's easy, handwritten digits, nobody cares, then I have prepared this Your Turn notebook, where we're going to use a different data set, and we're going to use the CIFAR 10 data set. So CIFAR 10 data set is another, let me actually show you some images from my solution. Don't cheat though. No phones out. CIFAR 10 is, so there's all these like canonical data sets in the deep learning community. MNIST was sort of like the first one. And you know, the best networks now get like basically no errors in MNIST. CIFAR 10 is a little more difficult. It's images, it's color images, so that's the first big differences. It's color images, not very high resolution, as you can see. I can barely recognize any of these things, but it makes it fast to run on your laptop, so that's great. And it's 10 different categories, so it's the first 2. So I just picked the first 2 here because it's going to be faster and easier to run on your notebook than all the 10 categories. So the first 2 categories are planes and cars, and then there's also, I think, like dogs and cats and whatnot. So the task is to recognize, well, is it a plane or a car? And yeah, so it's a color image, so it has 3 channels. So that's a big difference. So you have to think about how to change that. So I'll just run you through what the few lines that I wrote here real quick. So first up, you import all the things, you load the data set, then we're going to look at the shape of the data set, and we see it is 32 by 32 by 3 channels now. And then, so it's 50,000 images in the training data set, and then there's a trailing dimension here that doesn't make sense, so we're going to squeeze it out. Don't worry too much about that. And then we're going to pick the 2 first classes only, so that's now only the planes and the cars, and that's going to leave us with 10,000 images. And so your first task would be to visualize the data, like plot some images, then prepare the data. So you can use the MNIST notebook that we just used, but you know, there's a little difference because it's a 3-channel image. And then the task would be to build a fully connected network, how we saw it. So again, you can use the MNIST dataset as inspiration. There's going to be some things different now. So the first thing is, now that we only have 2 classes, before we had 10 classes, now we have 2 classes. So the softmax activation function and the categorical cross entropy might not be the best choice, because now we're dealing with a binary classification problem. So is it the one or is it the other? So maybe Google around and think a little bit about, try Googling for the Keras documentation, or Google around, or ask me if you're stuck. But you probably want to think about what you want to write instead of softmax and what you want to write instead of categorical cross entropy. Then check out the predictions. You know, it's going to get some of them right if you do it, but it's also going to get some of it wrong. And which ones are the ones that it gets wrong? Like, does it make sense that it gets these wrong? Just plot them, like figure out. And then if you get to this stage, try to get the best network data you can, and you probably want to use a CNN for that. And yeah, see how good a score you can get in the end. Yeah, so that's basically it. So that will conclude the first part. And feel free to start coding, ask me any questions, or leave. Take a break as well. And yeah, oh yeah, time-wise, I would say we go until around 12 and see how far we get, and then probably everybody wants to go for lunch. And so again, I've never done this before, so in this tutorial part, so we'll see how it goes. So you're kind of my guinea pigs. Sorry about that.